go in for larger bit adders, you have to go in for uh, a block of full adders, in fact. So there are two ways. Either you can do a serial addition or you can do a parallel addition. So we saw the disadvantages of a serial addition in the last class. So we just saw how to do a parallel addition. In the parallel addition, what you saw in the last class was that your carry here will propagate every time. So which means that the output across this sum, across this full adder block, you will get only after you get this carry here. Okay, so that is the disadvantage here. Okay, but with this particular disadvantage, it is manageable when compared to a serial bit addition. Okay, so why it is called as a parallel adder? Because your inputs are available all the time across all the full adders parallelly, and the output gets executed on the arrival of the carry bit from the previous full adder. Now, various applications of these parallel adders are available. So one such application we are going to take is a 4-bit parallel adder. Why 4-bit parallel adder? Because that is the immediate multiplication that we can do from a 2-bit full adder that we have just saw. So first let us understand the basics of a 4-bit parallel adder. So whenever you are doing any digital design, you must make sure that your system does not fail even for the worst case condition. So here always we have to keep in mind what will be the worst case analysis. There was one example some years back that when they designed the computers, somebody asked to debug if there is any problem or not. The CEO of the company came and he just smashed all the buttons in the keyboard, and then he found that the system got hanged. Right? So that is the worst case scenario that is possible. Right? So your system must take care of all such kind of worst case conditions under extreme uh, conditions also. So here also, what is the worst case condition here? We have to analyze. Least case condition, if you analyze, you can implement the circuit, but your system will always go and drive into a worst case problem. So here, first let us understand what is the largest result possible when you have 4 bits. 4 bits in the sense what? Let us assume that there are two variables here, A and B. So I want to add these two values A and B. A is a 4-bit variable and B is a 4-bit variable. Now, what are the possible answers? 1 plus 1 is 0. So you will get a carry. So result will be 1, you will get a carry. Again, result will be 1, you will get a carry, and this will be your C out. Now, this particular condition, so how many bits output you are having? You are having a 5-bit output here. Out of this 5-bit, this is your sum bit. All these 4 are sum bits, and this is your carry out, C out. Now, all these are carry bits here. All this that you are seeing here, they are all carry bits. So what about this particular place? This particular place is this will be your input, which we call it a C in. Either we can assume it to be 0 because we are looking for a worst case condition, right? So if C in is 0, then this will be 0. If C in, if this particular value is 1, then this will also be 1. So this is the worst case scenario. Now, how do you visualize a parallel adder? So whenever you visualize a parallel adder, don't bother about what is inside the circuit, whether it is an AND gate or an OR gate or an XOR gate. Don't bother about that. Always assume it as a black box. As mentioned here, visualize it as a black box, which is for a 4-bit adder. So I've got a black box here, which is a 4-bit parallel adder. What are the inputs? I'm going to highlight all my inputs as in yellow here. So my A is my input, B is my input, and my carry in here is my input. So here the variables has been changed, never mind. So all my x's are my inputs, x0, x1, x2. This is a 4-bit variable, and y0, y1, y2, y3, they are all my inputs. And at the same time, cin is my input. Now what are my outputs here? My outputs are, I have got a 5-bit output here, out of which 4-bit is a sum bit and 1 bit is a carry bit. So my outputs will be, since my sum bit is 4-bit, my bits will be S0, S1, S2 and S3, and my carry out will be C out. So this is how I'm going to visualize my 4-bit parallel adder is. Internal working of it's all based on the logic. You can have full adders getting implemented, so that we will come back later. Now, why should we go in for such a block level design? What if we are very much familiarized with using gates? What if we use gates? If we use gates, then what is the first problem statement? Problem statement is to find out to design a 4-bit parallel adder. So if it is a 4-bit, how many input variables will be there? Please look at the number of inputs here. X0, X1, X2, X3 are inputs. Y0, Y1, Y2, Y3 are inputs. Cin is input. So how many inputs are here? 4, 8, 9 input variables are here. 9 input variables. And how many output variables are here? Output variables are, there are 4 sums and 1 carry. So which means 5 output variables are here. You all very well know, immediately after identifying the input and output variables, what we will do, we will try to write all possible combinations here, right? So 0, 0, 0, 0, 0, 0, likewise till 1, 1, 1, 1, 1 in the last row. So likewise, for 9 input variables, how many input possible combinations are possible? 2 power 9 is how much? 2 power 9 is 512, am I right? Yeah. So you will have so many number of input and output combinations. And how do you create a k-map also for 512 output variables? You cannot keep on doing the QM method or a tabular method also, Queen-Mikulski method. So this is an improper design, or it will be very, very complex in fact. Hence, we are going in for such block level designs. So as I said, you will have you have to make your truth table with input and output variables. Input will have 9 input variables here, 9 input variables, and output will be 5 output variables. So 2 power 9 combination of input variables will be 512 entries will be here. So it is not possible for you to create a even k-map. So it will be a complex design. So what is an alternate design? We will look at an alternate design. In the above example, your simplification is really complicated. So how do you implement? The simple solution is, if you are having an if you want to design an n-bit parallel adder, then it will require n full adders. In this particular case, we want to design a 4-bit full adder here. So we need 4 full adders here. So how do we connect these 4 full adders? We will connect these 4 full adders using in a cascaded form. So you all remember how did we cascaded our 2 half adders to get a full adder, right? Similarly here, we will cascade 4 full adders to build a 4-bit adder. So here is the example here. Please look at the different variables here. So first, this is a full adder. A full adder, let me draw a separate block for a full adder. Maybe I don't have space. Yeah. So what is the block diagram for a full adder? If I have a full adder block, what are its input and output? My input will be 2 bits, right? Maybe X and Y. These are single bits. Okay. So X and Y are my inputs and C in will be my input. Similarly, my single bit output sum and carry, these are my outputs. If I'm having a 4-bit adder, I will represent it as x0, y0 and s0 and c0. Okay, so that is what is written inside this particular block. These are the blocks that are available from the manufacturer with the same variables that I have written. X and Y are from the manufacturers. Whereas I am using it for my design where my variables are. So I'm using my input variables are as A0. So since this is a 4-bit variable here, it is A0, A1, A2 and A3. Similarly, I will have B0, B1, B2, B0, B1, B2 and B3. Okay. And Cin is my input. And my outputs are my S0 sum, S1, S2 and S3. And you must note here that every block will have a carry, right? So this particular carry from the first full adder gets propagated to the second carry. So this is C0, C out from the first full adder. The output of the first full adder, which is your carry out, will be the carry in for my second full adder. So this carry, I'm mentioning it as C1. Similarly, from second full adder to third full adder, my C out of my second full adder will be C in of my third full adder. So likewise, and finally, I will get my C out, right? So this is how you have to create a 4-bit parallel adder using 4 full adders. Okay, any doubt in cascading it? Okay, now let us analyze the same thing slightly. Yeah, it is the same thing that has been given here. The inputs are two 4-bit inputs A3, A2, A1 and A0, and there will always be a carry bit also, right? So you've got two, so all these are inputs. All these are inputs and the Cin is also an input. All these are outputs, 4-bit output and your C out, this is also an output. What about this C1, C2, C3? This you will not get to know also. What does it mean is this will be your, I'm just drawing a dotted line here. This will be a complete 4-bit full adder, which you will see only these inputs. Whatever it is available output outside the dotted lines, these are the only things you will visualize. Which means that if I draw the dotted line as a solid line like this, what are the inputs and outputs I'm seeing? I'm seeing A input and I'm seeing B input. Please note that this A is A0, A1, A2, A3 and B is B0, B1, B2, B3. In addition to that, I will have C in. This is a 4-bit. If I write like this and write it as 4, it means that it is 4. I will get a sum and sum is also a 4-bit and I will get a C out carry. Okay, so I have not put a line across this input C in or C out because they are all single bits. Okay, all right. Now, whenever you want to perform a 4-bit addition, we are just taking an example. You let A is 1011 and B is 1110. The first thing that you must do is get the block and fill all the inputs in the diagram, including C in equal to 0. Then you must know that your full adder output 1 will produce your C1 and S0, right? So this will produce your C1 and S0. Okay. Similarly, your C1 will be used to find C2 and S1. Only if C1 arrives, you will have your C2 and S1. Otherwise, you will not get the output. Only if C2 arrives, you will have S2 and C3. Only if C3 arrives, you will have S3 and C out. So your output here depends on the carries that are getting propagated from one stage to the other stage. Okay, so this is called as a carry. So here you can see that the carry is propagated or cascaded from one stage to the other stage. Though these are called as parallel adders, why they are called as parallel adders is because the inputs are available all the time across all the full adders. Hence, these are called as parallel adders. And the other name of these kind of adders, they are called as ripple carry adder, because carry gets rippled from one stage to the other. So that is why these are called as ripple carry adder. Uh, Again, the disadvantage that you can see here is your output will be available only after all the carries are available. So which means that only if the carry arrives to the last stage, so then you can get your final output. So is there any other solution? The other, in order to avoid this, there is another solution. So what is that particular solution is, there is a technique called as look ahead carry, which means that you can predict what will be your carry without waiting for your final stage output. So we will look at this look ahead carry in a detailed manner. It is a complete one uh, class is required to understand the look ahead carry. So just remember this, the disadvantage of a ripple carry adder can be solved by using the look ahead carry adders. Okay. Now let us take an example. I said this before also. When we were designing a combinational circuit for BCD to XS3 converter, I said that instead of creating a truth table and then trying to get a K map, you can also use a block level design using full adders. That is, you can exploit the property of XS3. That is, XS3 is what? XS3 is nothing but the binary value or the decimal value plus 3 will get you the XS3 value. So you can exploit this addition of plus 3 here. Okay, so how do you do that? How do you do that is, again, this 3 corresponds to what? This 3 corresponds to 0011. Am I right? And this n corresponds to any binary value. If it is a 4-bit XS3 code, then it will have 4 bits. Maximum bit that you can have is 1111. Okay, so which means that you can have a full adder and you can add 0011 to it. You will get an XS3 code. Okay, so let us look at that particular design. So in the last lecture, we saw a gate level design was used for four input variables. I said that particular time itself that there is an alternate design possible using block level designs. So we know that XS3 code, if you want to convert whatever is the BCD code is, you will add 3 to it. So this can be represented as your XS3 sum. If you represent as a, this can be represented as a 4-bit addition. Why 4-bit addition? Because this is a 4-bit variable. Only thing is, it is not a variables. This is a standard value. BCD is again a 4-bit variable. So what you are performing here is a 4-bit addition here, and the output that you get will be S0, S1, S2, S3. Now there is one more addition here. Cout will be there, but we will not use that particular Cout. Why we will not use that Cout? Because what is the maximum BCD value possible? Maximum BCD value possible is 9, 0, 1, 0, 0, 1. What is 1, 0, 0, 1 plus 3? This is equal to 1, 0 is correspond to 12, which is 1, 1, 0, 0 is the maximum value that is possible, which will be taken care by this sum bits only. So Cout here we will not use, because carry will never be generated when you are using a XS3 to BCD converter using full adders. Okay, so if you consider this 3 binary value 3 as B0, B1, B2, B3, all you can do is you can use 4 full adders, because A variable and B variable can be just added by using a 4-bit 4-bit parallel adders. So if you want to use a 6-bit full adder, you can just easily expand here. Okay, so a 6-bit conversion, if you want to perform, then the sum bits will be S0 to S6, and the BCD values will be from A0 to A6, and your this addition plus 3, it will not change. Only thing that will change is 2 zeros will get added to it, because this is a This is a constant value here, plus 3, right? So you can use 6 full adders to implement the same thing. Now recall, if you are doing the same thing using a gate level design, then for the gate level design, you will have 6 variables on your as a BCD input and 6 variables on the XS3 output. You have to write all 6 possible combinations, so 2 power 6 possible combinations, close 64 possible combinations, and then you have to write the XS3 code and look at the K map that you need to simplify. It is a complicated process. Now this will simplify, the block level design will simplify the, either you want to do a 6-bit, 8-bit, 10-bit, it is very easily implementable now. So if we want to represent the BCD to XS3, sorry, XS3 to BCD, I'm sorry, BCD to XS3 converter using full adders, all you need to represent is just a block diagram, which is a 4-bit full adder where the B variable inputs are given as 0011. You give a constant input as B3 as 0, B2 as 0, B1 as 0, and B0 as 1. And your carry is also 0 because your input carry here is 0. And A0, A1, A2 corresponds to the BCD inputs. Your outputs will be your SS3 output, and you will not use this Cout at all. Okay. So likewise, if you want to perform a 16-bit parallel adder, then definitely 16-bit parallel adders are possible. Let us take an example. So please remember now, first we designed a half adder. Then we designed a full adder. In full adders, we used half adder. Then what we designed 4-bit full adder. In this 4-bit full adder, we used this 2-bit full adder. Then what we are going to do is we are going to design now 16-bit full adder. In 16-bit full adder, what we are going to do is we are going to use this 4-bit full adders. So one such example here is, this is a, let us take an example here. Construct a 16-bit parallel adder. Now, as I said in before, I created a block diagram here, right? What is this? This is a 4-bit full adder. This is a 4-bit full adder. What are its inputs here? 4-bit A, 4-bit B as carry in, 4-bit sum out, and C out. These are our inputs and outputs of a 4-bit full adder. If I want to use a 16-bit full adder, I will use this 4-bit full adders 4 times, and then I can implement a 16-bit full adder. So this is what I have done here. Look at the blocks. Look at the block. If I have 16 bits, then what are the inputs possible? It is, if I use X as my variable here, X0 to X15 is my X variable. Y0 to Y15 is my Y variable. C in will be my input variable. S0 to S15 will be my sum variable, and C out will be my output variable. Okay. And what are your internal carry bits? Your carry bits will be, what is the output of this full adder? If this is C3 here, this output will be C4. Please note that we are going to cascade it, so we cannot have C out here. So this will be C4 here. So the output of, so instead of C out here, let me write C4 here. So the output of the carry output of a 4-bit full adder here will be C4. So we are going to exploit that. So this is the one 4-bit full adder here. As you can see here, I have written a cross here representing that this is 4-bit ranging from Y0 to Y3. Again, this is 4-bit ranging from X0 to X3. So C0 corresponds to the, instead of C in, C0 has been used, which doesn't talk. C0 is nothing but your C in. So the output here will be C4. And if I can use the same block again and connect the C in input to this C4 here. Similarly, this C in input, what will be this second 4-bit full adder's output? You will have, okay, the first sum will be S0 to S3, S4 to S7, S8 to S11 and S12 to S14. And the C16 will be your actual C out. Okay, so this is how you create a 16-bit full adder using a 4-bit parallel adders. And I've already mentioned here that if I mention like this, it means that this is a bus bar. We call it as bus bar. Okay, it is a combination of bit lines. So this is equivalent to 4 lines connected parallel: S0, S1, S2, S3. Okay, don't worry about this. This is a very long assignment. This is not for you. Okay, the disadvantage of this design. What is the disadvantage of this design? If you want to look at the output of the C out and all the sums here, you have to wait for this carry here's getting propagated from one stage to the other stage. Here you just look at only 4 block. Each block has got 4 full adders and each full adder has got 2 half adders. Okay, so look at the delay that will happen when you are performing when you are going in for such 16-bit parallel adders. So that is the disadvantage with these kind of adders. Now let us take another example, an adder cum subtractor example. Now first let us we have seen adder now, right? We have seen 4-bit adders right now. Even 16-bit adder also we saw. So we are very much comfortable with designing an adder. What about an adder cum subtractor? Okay, now so first let us understand how we are going to perform the subtraction. Here for subtraction, we are not going to use full subtractor. If you remember, we always in digital electronics, we always performed our subtraction using addition. So we are going to use the same technique here. What is a binary subtraction is A minus B, which means that A plus the 2's complement of B we used to write, or in terms of 1's complement, we used to write it as A plus 1's complement of B plus 1. So 1's complement, what is 1's complement of B? Just a complement of B. So which means that A minus B can be written as A plus B bar plus 1. So B bar is nothing but the complement of the variable B. Now, how do you perform addition? Addition is simple: A plus B. Now you compare these two equations. A plus B is addition. A plus B plus, let me write it as 0. Okay. A plus, because now you will understand why I wrote 0 here, because I'm having for subtraction, I have to perform A plus B bar plus 1. So now I can use full adder for this, right? I can use 4-bit full adder for this, am I right? Because this is a 4-bit addition. So if I use a 4-bit full adder, this is what my block will look like. I have got for A variables, I have got A1 to A4. For B variable, I've got B1 to B4. Don't get yourself confused if I'm writing B0 to B3, A0 to A3. Don't get yourself confused. These are variables. But it is a good practice. You can have it when you are cascading like this. It is a good practice to not include 0. Okay. So here I have not included 0 here because that might create confusion later on. So that is the reason. Okay. So what is the other inputs of a 4-bit full adder? The other input of a 4-bit full adder is your carry in. Now here I'm using my carry in input as my control signal yes. Okay. So this control signal yes will tell me whether I'm going to perform addition or subtraction. Let me write the equation. For subtraction, the equation is A plus B bar plus 1. For addition, my equation is A plus B plus 0. Okay, which means if my control signal yes is 0, okay, here I can perform addition. If my control signal yes is 1, which means my Cin is 1, I have to complement this B1 to B4. I have to complement this and then I can perform the subtraction. So A part, there is no worry about it. There is no worry about this particular part. I have to create a logic to implement this particular part. So how do I create a logic? So when S is equal to 0, I have to perform addition. When S is equal to 1, I have to perform subtraction. So if I create a logic B and S, when I can implement the same thing using an XOR gate. How XOR gate? When my sum is 1 here, when my sum is 1 here, or I'll come back to the XOR gate later. So what if I use an XOR gate, one input is B and other input is 0. Okay, what will be my output? My XOR gate output will be whenever my both the inputs are same, that is when one of the input is 0 here, okay, and your output will correspond to the B variable. My output will correspond to the B, or if you want an XOR gate truth table, I can write it separately here. I will write it here. So 0, 0, 0, 1, 1, 0, 1, 1. When the inputs are same, you will get 0, else it is 1. So when my sum is 0, when my sum is 0 here, as written in the red, my output will follow my input, right? So here also it is 1 is 0. Here also it is 1, 0. But if my sum is 1 here, that is corresponding to these two cases. Corresponding, my output will be a complemented form of my input. So whenever I'm having 1 here, I'm getting 0. Whenever I'm having 0, I'm getting 1. So this XOR gate here, this XOR gate, when my S is 0, my output will be A plus B. When S is 1, my output will be B bar, right? When my S is 0, your output will follow as it is here. So I can use as a sum A plus B because it is sum is also 0. Here I can use it as A plus B bar plus this particular sum because S is 1, right? Because we wanted S to be 1. And this is S because and S is 0 here, right? So how do you implement this? If you look at the output here, when S is 0, my output will be B, and when S is 1, my output is B bar. So the same thing can be implemented like this. Don't, if it is in a blackboard, I could have drawn line by line, but never mind. Don't look everything in a single glance. Just look, as I say, A1, there is no problem, right? A variables, there are no problems. Now, if you look at the S variable also, no issues. S1, S2, S3, S4, and output is C5. Okay. Now the carry in is also fine. C2, C3, C4 is fine. Now, if I connect it this way, where I XOR my carry in with my B variable here, what will happen? If say my S is 0, S is equal to 0. My carry in value will be 0, right? And what will be the variable that I will get here? I will get B1 instead of B1 complement, because when my S is 0, my B will follow as it is across my output of my XOR. So when my S is 0, I will have B1 here, I will have B2 here, I will have B3 here, and I will have B4 here. So this full adder now will perform what? Will perform A plus B plus this 0. What is A plus B plus 0 corresponds to? Plus 0 corresponds, this is a addition that we would like to perform. Okay, now let us look at the other case. Okay, now let us look at the other case. When S is equal to 1. If so, my carry in will be 1, right? So which means my C in is 1. So let me write 1 here plus. If my S is 1 here, my XOR output will be a complement of my other input. My S is 1 here, right? So my S is 1 here, my S is 1 here, my S is 1 here and 1 here. The output of my XOR gate now will be a complemented form of my other inputs, B1 bar, B2, B3 bar and B4 bar. Okay, so which means that I get a complement of B. And what will this full adder will do? It will add my A and B complement, right? So what is that I've got? I will be getting the subtraction of across my S1, S2, S3, S4 variables. Any doubt here? Okay, so this is how you create logics. Yeah. So in case of this is using full adders, you can implement the same thing. If you look everything as a single block, then this is how you look at this block. So this is a 4-bit full adder written as a single block here. Cin has been connected to my control signal yes. When S is equal, it can take either 0 or it can take 1. And my input variables are A1 to A4 and B1 to B4 connected through an XOR gate. And my sum or my difference will be S1 to S4 and my output. Okay. Any doubts? Okay. Let's take another application of combinational circuits, a magnitude comparator. Uh, Magnitude comparator, let us start with first 1-bit comparator. What does it compare? I will be having two variables, say for example, A and B are my two variables here. I will have three possible outputs. Either A can be greater than B, or A can be equal to B, or A can be less than B. So based on the input combination, when it is a two variable, then you have four input combinations, right? Based on this, you will get an output. So I have already created a truth table here, a 1-bit comparator. If X and Y are the input variables, the four possible combinations of X and Y are 0, 0, 0, 1, 1, 0, 1, 1. And my output comparators are X can be greater than Y, X can be equal to Y, or X can be less than Y. So when it is X is 0 and Y is 0, only possible combination is this X equal to Y. When X is 0 and Y is 1, Y is greater than X, which means that X is less than Y. Similarly, when X is 1, which means X is greater than Y. When both are same, then they are equal. So now we have to write the truth table, or we have to write the Boolean expression for this. This variable corresponds to what? X greater than Y corresponds to X Y bar. So X Y bar for X greater than Y. This variable, this one corresponds to X bar Y. So for X less than Y, it is X bar Y. For X equal to Y, it is X bar Y bar plus XY. Okay. So what is this? This is equivalent to a NOR gate. So X bar Y bar plus XY is equal to a NOR gate. Now, if you implement this using a gate level design, this is how your gate level design will look like. So my inputs are, this is my input X and this is my input Y. So here it is Y bar here. So it is X, Y bar and gate. And this is X bar. The output here is X bar Y. So here it is X nor Y, which is equivalent to X equal to Y. So all these four equations here are implemented using a gate level design. Okay, so this can be extended for a multi-bit numbers also. Multi-bit in the sense this is just a 1-bit number. This is just a 1-bit number. Now, how do you extend this to a multi-bit number? Okay, so We will continue this application maybe in the next class. So for a four, okay, yeah, this also requires some kind of an exclusive thinking and understanding. So we will continue this multi-bit magnitude comparator in the next class. Uh, okay, so is there any doubts? Okay, so if there are no doubts, you may exit the meeting.